Hey guys, it's Simon and welcome back to another part of the LibGDX Kotlin tutorial series. Long time no here. So in this part we are going to develop a day and night system with the help of Box2D Light, and I'm quickly showing you what the end result will look like. So this is our normal map that we would have. So everything is as we had it before, so player movement, AI movement and everything. But now when we press the N button for night, then the lighting in the game will switch to a night theme, and when we press the D button for day, then it will go back to the daylighting. And with that, as you can see, we can then also cast these shadows and have some nice scenery and ambient light and all of that. And it's not that difficult actually, because we are already using Box2D, the physics system. And with Box2D, there is then also the Box2D Light library. And with that library, we are then going to create this kind of light effect. And what we're going to have is that the player will have a point light. It's called like that because it's a point. We will add a little bit of, like, I call it the breathing effect. So you see that the light goes slowly out and in, and it's not just a static light. Then also the enemies have a light. The chests and other environment stuff, they don't have a light, but they will then throw the shadows accordingly. And I think that's it. So if you are interested in that, then please stay tuned. And otherwise, please also stay tuned to learn something new. So as mentioned, we are going to introduce a new library, which is called Box2D Lights. And it does not have its own homepage from what I see. So at least I couldn't find anything in Google. But in order to work with it, we need to add it to our build Gradle file in the core project. So simply there, go to core and then to the build Gradle file, and then add a line to it. So like this, so we have combat logic games, then it's Box2D Lights, and then a specific version. And this version we need to define in the Gradle properties file at the root. And there we can simply use the version 1.5, which should be the latest version. I will add a link to the GitHub repository if I can find it in the video description below. And then simply refresh your project, then Gradle will download everything, and then we are ready to use Box2D Light. And as mentioned, it is a library to create lights. So there are different kind of lights. So from what I know from the top of my head, there is a point light. There is also a cone light. And I think there are 2 or 3 other lights. Let me quickly check. So there you have it. There's a point light, there's a directional light, there's a cone light, a chain light, a position light. So different kind of lights that you can then create. And the core class of this entire library, I would say, is then the so-called RayHandler, which is then responsible to draw and render all the different lights that you create, and also calculate the shadows and so on in the Box2D physics world. And all of that is working with a so-called FBO, which is the short term for frame buffer object. We did not use that yet, but you can imagine it like the name suggests. It's a buffer of 1 frame. So when you render something, your entire scene with Box2D physics bodies, then you can imagine like this RayHandler uses then a separate buffer of this frame, so as a separate buffer where this scene gets rendered to. In there, it then calculates all the lights that we have created, so the different lights and also the shadows in it, which gets then stored in a separate texture, which would be this frame buffer, and then simply that buffer gets rendered over your normal scene with specific blending options. And the light and shadow texture in itself, you can simply imagine it like a black and white texture with some grayish colors in it. And because of the way that the blending will then works, you get then this effect that you saw before in the demo. And here you already see, so in the RayHandler, there is this diffuse blending function, and there would be also some other blending functions. You can check that out yourself if you are interested into that. But the important part for you to know is that there will be a frame buffer used, which is per default, it's a quarter of the entire window size. You can resize it. I will show you that as well. The difference that it makes is that the lights get then sharper. So if you have a game with a bigger resolution, then I would suggest to also resize the frame buffer accordingly. But for our pixel graphic game here, we don't need to touch that at all. So we just simply keep it as a quarter of the window size. And then, as mentioned, the important part is that we have this frame buffer, and together with a blending function in OpenGL, we then simply render the the buffer of the lighting texture and the game scenery, they get blended together, and the final result is then what we saw at the beginning in the demonstration. Good, so the first thing that we want to do is to create an instance of this RayHandler. So we go to our game screen where we have created everything, and then simply at the top, there we will create, maybe after the physics world, we will create this RayHandler. So we will have a new instance of it, which we will simply call a RayHandler. And the RayHandler is then a new RayHandler instance. And that one takes as an argument so the physics world, so that it knows how it needs to calculate the shadows and the lights and everything. And that would be our physics world that we just created a line before. And there you see it, you have this frame buffer width and height. So this is the size of the texture that will be used for this light rendering. And there we simply don't touch it. And by default, if I remember correctly, it's a quarter of the screen size. So as you see here, it takes the width of the graphics and the height, which is the screen size, and there divides it by 4. So that would be the size of the frame buffer. And for our pixel game, that's totally fine. If you have a game with higher resolution and better textures maybe, then I would most likely adjust the frame buffer. But for me, personally, I never had to do it. Okay, and we also want to adjust the RayHandler a little bit. I show you the differences then when we going to implement it, that you see it then step by step. But one of the things that we want to set is the diffuse light, which we are going to say to set to true. And the difference here is that normally when you don't use a diffuse light, then the lighting, especially the white lights with a white color, they get extremely bright in my opinion, and it does not look that good. I will show you the difference then, and the way to fix that is that you simply don't use a diffuse light. So there also it's a typical term from what I know when it comes to game development and lighting, and there you can look up exactly what diffuse lighting does for you. In this 2D environment, for me always I prefer to use the diffuse lighting to get then a better result. But as mentioned, we see that then later on. And it's important here that this is actually a static method, so it's not really a method called to our RayHandler instance. It's a static call to the RayHandler, but I still want to keep it in that block because I think it's grouped together and it's a little bit better in my opinion and easier to read. Okay, and then one important function is the so-called set ambient light, and this is simply the color that will be used which blends into your entire game scene. So for a night light, for example, you want to have a dark light. So if we would have, for example, black, then we wouldn't see anything at all because then the black color gets blended into our scene. And since black does not have any color, let's say, so everything is 0, red, green, blue, so we won't see anything of our game scenery. But if we use, for example, a dark bluish color, then we get like a night effect that we saw in the demonstration. And just for now that we see something, we will use one of the built-in colors from LibGDX, and we use, for example, the royal color, which is a bluish color tone. Okay, then we of course want to work with this RayHandler, so we add it as an injectable to our entity world so that we can use it in the different systems. Then we also want to do something when a resize is happening. Do we have a resize method here? It does not look like it, no. So let's override that. So we will implement a resize method. And what we want to do here is that we want to call a use custom viewport on the RayHandler. I had initially in my first project where I used Box2D Light, I had some problems with the way the lights got rendered, especially when I was resizing the window and using some special custom viewports. And took me quite some time to find out that there is a method which is called like that, so use custom viewport. And in there you can then set the boundaries of the viewport that you are using for your game to align it then, of course, with the, you can imagine it again like this frame buffer texture in the background, that everything gets then rendered in correct relation to each other, and when they get blended together, that the lights are then really at the correct position. So for example, later on we will attach a light to the player body, and of course this light should then be in the center of the player and not somewhere with a specific offset. And to fix that, we will call this use custom viewport. And what we need there is we need the screen X, screen Y, the screen width, and the screen height of our viewport. And the viewport that we are going to use for our game is from our game stage. So there we have the viewport. And there we can then get these values. So we have a screen X. Let's store it like this and then just copy it 4 times for now. Then we have a screen Y, a screen width, and a screen height. And that would be here the screen Y, the screen width, and the screen height. And that would be it. And finally, of course, so RayHandler, again, similar to a physics world, needs to be then disposed safely, because at least the frame buffer object, from what I know, that is a disposable object, so that needs to be disposed. And maybe there are some other things internally, most likely the light objects or instances itself, they also need to be then disposed. So don't forget to call the dispose method on your RayHandler to clean up the resources properly. Okay, and then I noticed something in the GitHub code as well, and I think we did the same mistake here as well. So in our game class, so the Mystic Woods YouTube, there we have overruled the resize method, because the game stage and UI stage need to be resized anyway all the time. And since we don't make here a call to super, so let me simply add it here. So what is happening in the default implementation of the KTX application, it will call the resize method of the current screen, and we are currently missing that. So we have overruled overridden the resize method before in the screen, but it wouldn't get called. So actually this code would never be reached. And to fix that, we need to add here the super call in our game application so that the screen resize method gets correctly called. And it's important to actually call it at the end, because here we are updating the viewports with the new width and height of the window that we get. And in our game screen resize method, we need to get already the updated values of the viewports to pass it then correctly to the use custom viewport. So make sure that the resize method, so the super resize method, is called at the end here after we have updated the viewports. Okay, and then I forgot to zoom in a little bit, so I will zoom in the codes now that you see it a little bit better. Sorry for that I forgot it at the beginning. And then, as always, what do we do when we add some new functionality to a game? We add a new system. So we are going to create a LightSystem, which for now is an interval system normally. So for now it does not iterate over any entities, but it will do that then in the near future, because as mentioned at the beginning, we will add some sort of a breathing effect so that the light goes out and in, and that is not built into Box2D Light. We will implement that ourselves. It's not very difficult, you will see that. But for now, we focus just on this ambient light that we have added for now, that we see the difference between our normal scene and now the new scene when we add the RayHandler. So let's implement that one here. So what we need is, first of all, of course, we need our RayHandler. Since we added it as an injectable before, we can add it here as well. Later on, we will then also get a new light component, so we need a new component mapper, but for now, we are not interested into that. Then we need some attributes so that we get this fading effect between day and night. So there I use the interpolation functionality again from LibGDX, and it simply changes from day to night over 2 seconds, and backwards also from night to day over 2 seconds. And to do that, first of all, we need let's call it an ambient transition time, which by default is 1. So when the value is 0, the transition is starting, and when the value is 1, then the transition to the new ambient light is finished. So initially we don't want to transition anything, so we'll keep it, or we set it to the value 1. Then we have the current ambient color itself, so that will be a new color instance of LibGDX, and there for now, let's set it just to white. So red, green, blue is 1, and also the alpha value is 1, and that's it. And then we need an ambient color from, and we also need an ambient color to, so that we have a starting point for our interpolation and also an end color for our interpolation, so that we really transition between those two colors. And for now, we simply add it here as a companion object, and there we add 2 specific colors. So we will have a day ambient light, and we will have a night ambient light. And for the day, we also simply take a white color, where we can actually, let's reuse here the things that LibGDX has built in. So we use the color white, and for the night, let's use the color royal, that we see that. And here just to initialize it, so that would be, for example, from day, and we want to go to the night. So just that we have some initial value for the color. Okay, and then we are going to implement the onTick method. And here we are going to check simply, it's just more like a debugging, let's say. So when the key is pressed, and the key will be the N key, and the ambient transition time is 1, which means there is currently no transition in place. Then we switch from day to night. And the other way around, when we press the D button for day and there is no current transition, then we switch back from night to day. And what we do here, so here the ambient transition time will be then 0. Then since from would be the day ambient light, and 2 would be the night ambient light. So we go from day to night when we press the N button, and similar here below, when we press the D button, then we go from night to day. Okay, and here we are going to implement something. So when the ambient transition time is smaller than 1, so the transition is not done yet, then we are going to update the time, which is simply the current time plus the delta time. And then to not make it happen within 1 second, let's make it within 2 seconds. So we multiply it here with 0.5 so that it takes 2 seconds instead of 1. And we also want to make sure that it's at most 1. Because the interpolation in LibGDX, not sure if I explained that in the previous part, but it expects a value between 0 and 1. So we need to make sure that we don't exceed the value 1 here. Okay, and then we are going to update our actual ambient color here. So the red value will be then the interpolation function that we are going to use. Let's also set that here below. So let's call that interpolation. And that would be the smoother interpolation, for example. We are going to use then the same interpolation function for this breathing effect of the light, and we are going to use the same one for this transition here. So here we are going to call the apply method. The start is always the ambient from red value. We are going to ambient to red value, and our alpha value is the transition time. And the same we have for green, blue, and alpha. So let's mark that here. So we have it for green. We also have it for blue, and we also have it for the alpha value. And finally, we just need to set the ambient light to this ambient color that we are going to calculate. And that would be it. So there we have a very simple light system where we can switch the ambient light from day to night and from night to day. So with this new system now, let's go back to the game screen and edit somewhere. Since it's related to Box2D, I simply edit here after the physics system, so that in here we will then update this ambient light, and also in the future then the lights itself, so the point light and so on. And the last thing that we now need to do, because currently we are just setting some values in the RayHandler, but we don't do anything with it. So the last thing that we need to do is now update our render system. So also in here we get our RayHandler. And now you will see how easy it is then to get this lighting effect to your game. So there we simply make here, so before we render the user interface, but after we have rendered our real game objects, there we will make a call to the RayHandler, to the set combined matrix, and there we pass in our game camera, so the orthographic camera, and we will also then call update and render, which is then updating the calculations with the lighting, and also then rendering to this frame buffer for the lighting texture, and then blending it together. So whatever we have rendered here before and everything that gets then rendered here to the frame buffer, those two things get combined together with a blending function, and that is then what ends up on the screen. And with that now, we should already be able to switch between day and night. Let's see. Okay, so I have muted the game sound, but as you already see, so we have now this royal color, so this bluish color is now on top of our entire scene. So this is the magic, let's say, or this is the functionality of this ambient light. And when we press the D button, we should now go back to the daylight, which is great, which is already working. And when we press the N button, then we should go back to this night light. And as you see, the user interface here is not affected because our rendering, if you remember with the lighting, is happening before the user interface gets rendered. Just that you see that, let me quickly switch that around. So let's do the RayHandler calling after the user interface gets rendered so that you see the difference here. Because some games want to have that as well. So you see already here the result. So the user interface gets affected here as well. So it also gets darker here at night. And if that is what you are aiming for, then of course, let's now you know how to do it. Simply call the RayHandler stuff after your user interface things. But if you don't want to do that, and this is what I was aiming for, I did not want to adjust or change anything in the user interface. That's why I did this RayHandler calling before the user interface. Good, but that's already it. So the ambient light stuff is already done. Let me switch that back here. Good, then the next thing would be that we need to create, of course, a new component as well. Didn't we miss it? So let's create a new light component. The light component is a pretty simple component, I would say, so it doesn't have a lot of information. It has a distance, which is actually the distance of the point light, so how far will it go? And since we want to have here this breathing effect, we don't need just a single distance. We need actually a minimum and a maximum value for the distance. And for that, I used a so-called closed floating point range, which we have built into Kotlin. And there I use a float value. And as default, for example, it goes from 2 to 3.5. So this is how you would define the range in Kotlin. And you see here already with this inlay hints that this is the inclusive value and this is also inclusive. So it's really between 2 and 3.5 and both values are inclusive for the distance. Then we need similar that we have with the ambient transition. We also need here a distance time, which is also a float. And here by default, it's 0. And finally, we have a distance direction. To keep it simple, it's just an integer, and per default, it's -1. The direction means, so if it's -1, it means that the distance here will go downwards. So in this case, it would go down to 2, wherever the value currently is. And if the distance direction is positive, so +1, then it goes towards the maximum, which would be 3.5 in that case. You could also, of course, here use, for example, an enum to just have 2 values. Go in and go out, for example, for the light. But here, to keep it simple, I just used an integer. -1 again means go downwards, and +1 means go outside, so that the distance gets greater over time. And of course, what we also need, which we cannot initialize immediately, would be a light, which is a box2D light. Then, similar to a physics body, we need to clean up a light, which means when an entity gets removed from our world, we also need to remove the light if it had a light component. So for that, we need a light component listener. And we don't need to do anything when the light gets added. So this method is simply a unit, so it does nothing. And when the component gets removed, then as mentioned, we need to destroy the light. It's called remove here. And as you have seen, so there are 2 methods actually, one without a parameter and one where this doDispose needs to be set. So if the light should be really then disposed. And if you don't pass a value here, as you see, the default implementation is that it passes then true to this doDispose stuff. And then it simply cleans up everything, all the resources which are related to the light. Okay, and this component listener, as always, let's not forget it. We need to add it, of course, to our entity component world. So here we already have some listeners, and let's here also add a light component listener. Great stuff. So we have that here as well, and the component here itself, I think is also almost done. What I did here, I defined a default light. So let's call that here a light color. And here I did not use the complete white color. I used here something with a little bit of a transparency. So for the alpha value, I used 0.7 instead of 1, which would be the case if I use color.white. Here I use a slightly different color for all the lights that I'm going to create in the game. Okie dokie, then we need to update our light system here now. So we are now going to iterate over all entities which have a light component. Then we need to change that here also, of course, to an iterating system. And we need to implement then the onTick entity method. And also here we need to make sure that we call onTick here of the interval system, or of the iterating system, so that this onTick entity gets properly called. And we do that simply before we do all the ambient stuff, but in that case, it doesn't really matter. We could do that afterwards, but we can also do it before. Okay, and we of course need access to our light component. So you know the drill. Let's add a component mapper for the light component. So we should have everything now in hand to create now this briefing effect of the PointLight. We haven't created the PointLight yet. That comes then in a moment. But one argument of the PointLight that we are going to create is the distance. And we want to adjust the distance of the light over time. So similar what we did here, we are going to do that now for every light that we have. So what we need the light component. And then we need the different properties from our light component. So there we need the distance, the time, the direction, and the light itself. And all of that we get out of the light component. One thing here, I think in the tutorial so far, I never used the destructuring functionality of Kotlin, if I remember correctly, of the data classes. But in my newer projects, also with the version 2.0 of Flex instead 1.x that we are using here in this tutorial, I use the destructuring a lot, and I like it, to be honest, because I think it's very convenient to get the different properties out of your component without always writing component dot, component dot, component dot. So here you can do it in a single line and get everything out of it. So that's why I used it more in the past, and also from now on I use it more. So I thought, why not also introduce that here now in this tutorial so that you see that. But we have a problem. The Kotlin experts of you might already know it. The problem is that we can destructure free properties here, but we cannot destructure the light here because it's not part of the constructor of this data class. But that is very simple to solve. So we just need to create a new operator function for component 4 in that case. That would return a light, and it simply returns the light that we have here. And now when we go back to our light system, yeah, perfect. So now this error is solved because we can now also get a 4th component out of it. Good, so the first thing that we need to do is that we need to update the time. So similar like we do it here with the transition time, we also need to do that, of course, for the briefing effect. And there it's simply the current time that we have plus the direction multiplied with the delta time. So here comes this direction into play. And this distance time is now a value that always goes between 0 and 1. 1 meaning that we have the maximum direction of our range here, and 0 would mean that we have the minimum value of our floating point range here. Okay, and this needs to be then coerced between 0 and 1, so that again we are passing correct values then to the interpolation function. Good, then we have a special case. So if the distance time is 0 or the distance time is 1, then we need to change the direction. Whoop. So from our light component, the direction gets multiplied with -1 to change the direction from in to out and from out to in. And then finally, from the real box to the light, we want to set the distance here. And there we use again our interpolation function, apply something, and that would be from our distance the start value, then from our distance the end value inclusive, and our alpha value would be from our light component, the distance time. And that would be it. So now we would set this distance of the light that we also see then in a moment. We also change that here a little bit. So we go between a minimum and a maximum distance with this interpolation technique that we are using here. And it's very similar to the one that we used here at the top with the ambient light. Good, so the next thing we need to define what kind of entities should have a light. And for that, we are going to modify our spawn configuration. And there simply add a new property. Let's call it, for example, has light. That would be a Boolean. And per default, it's false. So that none of the current entities get a light. And we want to change that now so that for the player and also for the slime, they should have this property set to true, that they then get a light component. So for that, let's switch to our entity spawn system. Then here in the player configuration, we say here has light is true. And also for the slime, we also say here has light equals to true. And then when we are spawning our entities, let's do that here after we assign here the physical component. So here, if the configuration has light, then we are going to add a light component to such entities. And there, to keep it simple, but most likely you also want to make that part of your configuration. But let's say that the distance here would be 5 to 6.5. So that those are the values that are used in a GitHub repository. And it's the same for the slime and for the player. But most likely in a real game, I don't know, for the player, you want to have it flexible, like the light radius in Diablo 2, for example. And maybe enemies should have a lower light radius or distance. So you would most likely put that into your configuration. But again, here to keep it simple, we just work with those fixed values. And finally, we are going to create a light. And as mentioned here, we are going to create a so-called PointLight. And make sure that you are using here the Box2D light and not this 3D stuff here, because we are working with Box2D light. Okay, for that, our light needs the RayHandler and it needs the amount of rays that should be used for the light. So the more rays you have, then the better it looks, and the less rays you have, the more pixelated it will look like. The value that I use normally for my pixel games is 64. Don't ask me why, it's just a value that I came up with and which I think looks good. Oh, and I see we did not add the RayHandler yet to the system. So let's also quickly fix that here at the top. We also need here the RayHandler. Okay, but we are not happy with just those two arguments here, because our light, we also want to set a specific color. So we are going to set from our light component, we defined this light color that we are going to use. So this whitish color, which has just a different alpha value than the normal white color. And the distance where it should start would be from the distance that we have defined before, and there just use the maximum, so the end inclusive. And X and Y doesn't really matter, we just pass in here 0. You could, of course, place those lights anywhere in your map, so that is why you can pass in here a position in X and Y, but we don't do that because we are actually attaching those lights to a Box2D body, which means that the light is always centered on the body itself and also moves around with the body. So this information, the X and Y information, we can simply skip it. And then, as mentioned, so what we are going to do with this light, we are going to attach it to a body. There you can also work with some offsets. So I don't know, if you want to add the light to over the head of your player, for example, then just work with these offsets. But we don't use that here, so we simply attach it to the body itself. So the body we get from the, yeah, okay, we have that here. So from the physical component from above, and there we have the body, and that would be it. So let's try that out. So in theory, our player and also the slimes should now have a point light if we did not do any mistakes. Let's see. And we should also have this breathing effect of the light. And looks good. So of course it doesn't look good because there's a problem, but I knew about that one. But as you see already, so when we move around, the light is moving with us, so that the player has this light here somewhere. Unfortunately, as you see already, the light is not going to the bottom, so the point light is actually just at the top, and it looks like it's colliding with the player body itself, which it actually does. So that's why we have this problem that the light does not go down here, but we are going to fix that in a moment. But you also see that here the light goes in and out. So we also have this breathing effect in here. And also just to show you the difference. So let's quickly, in the LightSystem, let's most likely just comment out the super on tick. So nothing gets updated here then. Let's see if that works so that you see the difference without the breathing effect. Yeah, so there you see it. So then it's just a static light, I would call it like that. And I think it's also, of course, a nice improvement for certain sceneries in your game, especially at night. But I like it more when it's a little bit moving because it gives some sort of a simulation like you would hold a lantern or something. And I just like it. That's why I usually add this breathing effect to my game. And yeah, I think that's it. You also see that this shadow casting here is already working when we are close to an object. Also here we are going to fix something because as you see, when we move away, at some point, as you know, we are going to despawn the collision objects. And when they are despawned, then of course we are also not throwing any shadows with our light because there's nothing here that would cause to calculate some shadows. So that's where also here we need to do a small adjustment. So those are the two problems. First of all, our light gets blocked by the body itself where it's attached to. And also we don't want that our collision bodies are despawning that frequently or that fast. Those are the two things that we are going to fix next. Okay, so one of the problems is very, very easy to fix. So first of all, let's add the super on tick again, that we have that available. And let's quickly switch to our collision spawn system. So there we have a constant, so the spawn area size, which defines when we are going to spawn and despawn certain collision objects. And here we reduced it to 1. But let's increase that back to, for example, 7, so that the objects don't get despawned so fast and that we then properly still have the shadows everywhere available. So if we now would start the game again, before, if you remember at that rock, when we got close to it and moved away, then the shadow also was removed because there was no body again to throw the shadows. But now, as you see here, so it remains here all the time and does not get removed anymore. So increasing it to 7, for example, that's the value that I use for the GitHub repository. That made sense here, and that already fixes the first issue, which was very easy. The next thing is a little bit more difficult, and I did not explain it yet, but in Box2D, so in this physics world, the way you can also define what kind of bodies are colliding with each other, and here in the context of Box2D Light, you can also define what kind of lights are like colliding with each other, which means which light is throwing a shadow from which object. And built in Box2D, they have this so-called category bits and I think group indices and one more, if I remember correctly. And with those bits, let's say, so it's a bitwise calculation, you can also define which kind of objects collide with each other. I personally don't like them a lot because I like it way better with the approach that we used in our collision handler, where I simply check the entities, what kind of components they have, and then based on that information, I tell the physics world if a collision should happen or not. I find that more intuitive and easier to read. But built in, as mentioned, and most likely also faster, would be this bitwise operation calculation where you can define that. And I did not find a way to bypass that in Box2D Lights. So that's why we're going to introduce here now these category bits to make it so that the player and the slimes, so those two lights, they won't interact with each other, so they won't cast shadows, which then solves the problem that currently the lights are actually blocked by the body itself. So what I mean with that, let me quickly open it up. So currently, as you see, the light is blocked by the player body here, same for the slime, so that's why we have the shadow here below. But we are going to fix that by giving this light a specific category bit, and then telling Box2D, don't make here any shadow calculation so that the light then passes through the player correctly. And on the other hand, we are going to add those category bits to the environment. So for example, to this rock or to this tree, for example, they will have a different category bit. And there we will tell Box2D Light that still the player light and also the slime light, they should interact with that. And yeah, as mentioned, it's working with these category bits. If you have never done that before, let me quickly explain it to you, because it's an important concept now that we need to understand. So I think back then, most likely in C, C++, maybe the origin is maybe from game development, I cannot really tell you. But to find out certain things, so if a certain criteria is set or not, to make that very fast, you can work with binary numbers, let's say. And in that specific case, in Box2D, we can define different categories, which should be a power of 2 numbers. So which would mean we start with the value 2, the next category would be 4, the next one would be 8, the next one would be 16, and so on. And these numbers can be represented in binary format. So 2 would be 1, 4 would be, let me quickly think, I think 0, 1, 8 would be, I hope I don't make a mistake, let me quickly think that through. Okay, I actually forgot here 0. So of course, 0 is 0, 1 is 1, then 2 is 1, 0. So that makes sense. Then we have 4, then we have 8, then 16 should be then 1, 0, 0, 0, 0. And you see here already a pattern. So there's always just one place in an entire column where we have, for example, here this 1. So this category 2, when we would check it against this category 4, for example, and combine it with an AND. So that one here, so 1, 0 and 1, 0, 0, that would be 0, 0, 0. Which would mean the smart friends out there and the computer itself, they know that it's not the same category, it's not matching. So that bit and that bit is not set in both numbers, let's say, to keep it simple. And with this kind of categorization, Box2D can very, very fast detect what kind of collisions, or in our case, what kind of light interaction should happen, because it then simply does these bitwise operations, which are, I think, most likely one of the fastest operations that you can do in your computer. But in my opinion, personally, I understand how they are working, but I don't like them because it's not easy to read. But as mentioned, I did not find a way to work differently in Box2D Lite. If someone out there knows it, please let me know. But yeah, for now it is what we have here, and this is what we need to work with. So we will create one category for the player, for example, which would be 2, then one category for the environment, which would be 4. And based on these categories that we are then setting on these Box2D objects, the Box2D Lite library then knows if it should interact with them or not. So with a specific filtering that we are going to set up. And yeah, long story short, let's implement that. Then I hope it makes more sense. Oh, and sorry, just to recap here, you could also use that, of course, in Box2D itself in the physics world, as mentioned. That way, there's also some tutorial out there, I think on iForce2D, if I remember correctly. And there you can then also define what kind of objects can collide with each other. But there's also a limitation, because I think you can go only up to 16 different categories, if I remember correctly. Maybe it's 12, I cannot really tell you for now. There would be a limitation with that, because that number cannot grow, of course, indefinitely. As you see here, it's getting quite big very fast, because you always need to multiply it by 2. And then you reach a certain limit. But yeah, if you like to think that way, then please use it. It's faster, of course. But otherwise, I personally suggest don't use it and try to avoid it, because no one else will understand what you're doing here. And I think our collision handler or contact handler is way easier to read and understand than this stuff here. So, as mentioned, we need to define some categories. So let's do that in our light component down here below. Can be a constant, and there we have, for example, a player category, which would be a short. This is the data type that Box2D is using, and that would be 2. Maybe you can start with 1. It would make sense that you can start with 1, but I'm not 100% sure, so I will keep it here at 2. Then we have another category for our slime. We could also call it maybe enemy instead of slime, but we just have one enemy, which is the slime, so I keep it with the name slime. And then we have another one, which I call environment category, and that would be 8. Okay, so now that we have these categories, what are we doing with them? So first of all, we need to go to our physics component, because there we have a method where we are creating the the body for the different environments. Let me quickly check. Is it this one? I think physics component from shape 2D. Exactly. So that one is called in the collision spawn system. And there we are now going to set the category for our fixtures. So here in our loop, we are going to modify it. And there is a so-called filter for every fixture. And there is a so-called category bit as well. And the category bit in that case would be the environment category. For the box below, we don't need to set that because the box is a sensor. And similar to box 2D physics world itself, a sensor does not interact with anything special. So it also does not cast shadows and so on. It's ignored by the calculation, let's say. But the loop here, which is the real shape, which is responsible for the collision handling with the environment, there we are going to set now this category. So this filter category here, also just that you have seen it. There's also, as I mentioned, this group index. If I remember correctly, it's then if you want to combine different categories to a specific group, then you can also work with this group indices. And then there would also be a mask bit, and the combination of category and mask bit with that in the normal box2D physics calculation or simulation, it would then know what kind of things can collide with each other. But again, I don't know the details. I don't like it a lot. So just that you have heard of it, those two things, so category and mask bit or group index and mask bit, with those two things, you could also define what kind of objects in your game can collide with each other. And again, that is most likely the fastest way to do it. But we don't need all of that, so we just need this category bit for now. Let's put that here in one line. And that's it. So the environment is already fixed. So there we have this category bit now. So we know that this specific loop has the category of an environment, which basically is the number 8. Then the next thing is our player and slime. So those categories we did not set yet, and that is part of the entity spawn system. So here, after we have created the body, we create a hitbox. There, just to be safe. So we could here check if it is a sensor. We don't need to set the category bit because, as mentioned, sensor does not participate in the simulation of the lights. But to keep it simple, we just set it all the time. So here again, filter, category bits. And here we would now need to set the category from the configuration. And the same is happening down below. So here for the collision box, there we also have then the category bit, which we need to set for the player and the slime. And we did not add that yet, so let's go back to our spawn configuration where we added this has light, and there we also need now to add the, let's call it physics category, which is a short, and by default it's, for example, 0. Good, and then let's go back to our entity spawn system. Let's define that. So for the player, we have from our light component the player category, and for the slime here, there we also have a physics category from the light component, and here it would be the slime. And now this physics category we can now set here at the top, so that we have the configuration and simply set the category from our spawn configuration. Okay, so we are now properly already setting the categories to the fixtures, but we did not tell box2D Light yet what kind of categories can interact with each other. And there we also keep it simple. In our game screen where we set up our RayHandler, there we can also set a so-called contact filter, if I remember correctly, which is again a static call. So light set global contact filter, which then, as the name suggests already, is a contact filter which is globally applied for your entire RayHandler. We can also, of course, set the contact filter for each individual light. So whenever we create a point light, a cone light, whatever, there you can also set a contact filter for that specific light. But in our game, we keep it simple. We just set a global contact filter, and that is good enough for us. And what we want to do, so we want that the player category, group index is 1, And the player should only interact with the environment category. That would mean that the player will cast shadows to environment fixtures, but it does not throw a shadow when it's interacting with a slime. And also with that specific filtering, we also get rid of the problem that we had before, that the body itself, where the light is attached to, that was blocking the light. Because the way we set up here the filter, we tell it that only the player is then casting shadows to the environment stuff. Everything else just calculates the light, but it does not calculate the shadows. And that should be it now again. Let's try it out. Okay, so looks already good. So our player here now has a correct light in all the different directions. As you see here, it still interacts with the environment. So there we get the correct shadows, also for the tree, for example. It does not throw any shadows for the slime, because that is the way how we set up the global contact filtering. So that is not, or that is working as intended. And I think that it looks good. What I did not show you yet is the difference between the diffuse light and the normal light. So here, imagine that specific scene now, and now we are going to switch it back. So now we say that we are not going to use a diffuse light, and I think we should see here a little bit of a difference. Yeah, so there you see it, that it looks then completely different, especially with this royal color now. So you see that everything gets super bright, actually, even if we would need now a different color. So it's, do you say that the opposite color? So we would need to subtract every value from our current color from 1 to get the same outcome of the scene that we had before, but you can already imagine it here. So you see that the sprite itself of the player is already brightened up. So it's a lot of brightness here now in this scene. I think in 3D environment, it makes sense, if I remember correctly, to get certain effects, but at least for me, from what I remember, for a 2D game, especially here in this pixelated game, it does not make sense to use this other light. We always use the diffuse light here to get the best result. Good, and that's it. So I think the complexity of using Box 2D light is not that high. The most complicated part is most likely with the setting up the categories that you get the correct result. But in the end, I think it's fairly simple to use when you know all the different methods that you need to touch. And especially you don't need to adjust the code itself a lot. So as you have seen, just to get the ambient light, it was just adding the RayHandler. Then in our render system, call this RayHandler update and render, and that was already it. Then you already get some nice light effects. So I find that pretty impressive and cool to use, and also, yeah, as mentioned, pretty easy to use. One last thing that I did not mention yet, but I had the problem there in my Mystic Garden project. Let me go back to our entity spawn system. There is one value that I did not mention when creating a light, and it's called set softness length. What I had, so the problem that I had was when the player was going to an environment, so for example, a cliff, then the light was completely blocked by the cliff. So the cliff itself was dark, completely black. And I did not want that. So what I wanted to have is that still the light is shining through the object itself a little bit. So shining through the other environment body. And you can solve that with this softness length. So as you see here, the default value is 2.5. What I used in Mystic Garden was 3.5, which was then a good result for me. But just that you heard of that, so if your light gets completely blocked by an obstacle and you don't want that, so that you want that the light is shining through the obstacle a little bit, then you can play around with that set softness length. Unfortunately, there is no good documentation, so I have no idea what 2.5 means. I think it's not the physics world distance. I think it's something else, and I haven't figured it out. But I just know that with that value, you can change that behavior, that your light goes through other obstacles a little bit. And that's it. Thanks for watching, and see you in the next part. Bye-bye.